So last class, we were talking about showing uncomputability of various languages, right? So we looked at halting. We showed that was uncomputable, starting with the toddler problem as uncomputable problem. Then we used it to conclude halt on 0 is uncomputable. Then we talked about not empty. And the way we were doing that is by this language of reductions. And what's the language of reductions? It's a way to reduce complexity or computability of one problem to the other. So specifically, reduction from A to B. Okay, so what does this mean? This means that you can think of it as I can solve A if I can solve B. Right? If someone gives me a black box for solving B, then I can use it to solve A. And the way we do this is by building this map, right? So there are various ways to do it. One specific way was to come up with this transformation. And what we wanted was, we should think of this as inputs for A, inputs for B. Okay. And the main thing that we need to satisfy is on any input to A, solving the problem A on a specific input X can be reduced to solving the problem B on the transformed input by R. Okay, this is the main property, and we need R to be computable. Right, so these are the properties of the transformation that we need, and once we have this, we have our punchline, which is if I can solve B, then I can solve A. And as a corollary, we can get two things. You can either interpret as a positive sign or by contrapositive, the negative sign. If B is computable, then A is computable. Right? If somehow I can compute B, there is a Turing machine for solving B, then I can use that machine combined with this reduction R to solve the problem A. And the contrapositive of this, which is how we often, many times use reductions, is if A is uncomputable, meaning A is hard, then B is uncomputable. Okay, so there are two implications of the same construction, really. Any questions about this? I know last class, when I was teaching this, I wasn't very clear. So I actually re-recorded that portion. And instead of re-recording only small segments, I re-recorded the entire last segment of the last lecture. But, if there are any questions about this, please let me know. Okay, and the main thing that you should keep in mind, and which is always a meta thing that confuses many people, and it is kind of non-trivial, is when we do these reductions, we are only transforming the inputs, but we're not kind of executing A or B or anything. We're just transforming the inputs. Okay. All right. So that's the summary of how reductions work. So today, what we're going to do is kind of prove one central theorem which implies many things about software properties. Okay. And I can say that, without a doubt, one of the main a main goal across many fields of computer science. You can take compilers, programming languages, you can take system design, you can take security, you can take computer architecture. In many of these areas, a long-standing challenge and goal is to reason about software, right? In some areas, your goal is just to write down the program. I want to solve this computational problem. Can you come up with an algorithm for it? But in some areas, your goal is always meta. I want to design a compiler. I want to design a better compiler. I want to design a better scheduler. I want to kind of do some real-time allocation of my architectural resources, all those things, right? So in all of these areas, you're trying to reason about software that is already part of the input, okay? So main goal, reason about programs. In many areas. Okay. And what kind of things would you like to know about programs? Any suggestions, any guesses? Like, what are some properties of programs that you would like to know? One we already saw. Is this program going to halt? That's a very important practical question. Unfortunately, we saw that it is not solvable. But how about something else? You can ask, does this program compute? Okay, this is like software verification. Somehow, let's say I'm writing an algorithm, which is just a program, and I'm going to put it on some chip and send it to Mars. And I want to know for sure that there is no bug in this program. It is supposed to multiply numbers. I'm not going to just trust some, some number of test cases that I inputted to verify that my algorithm is correct. I want bulletproof proof that it is correct. For example, does program, which you should think of as Turing machine M, compute, let's say, majority function. Okay. This is the whole area of software verification. In fact, it really revolves around this question and what we can do with this. You can also ask, like, are two programs equivalent to each other? Okay, so all of these things. And the main thing, you can abstract away from the questions arising in this area, such as programming languages, network security, computer security, software verification, many of these areas, is that there are questions not really about the actual lines of code that you wrote down, but the functionality of the program. I don't care, if your Turing machine has 10 states or 12 states. I don't care if your program has a variable named foo and bar, but I care about its input-output behavior. Does it actually compute multiplication exactly? You might use weird names in the program. That's fine for me. Okay. So to abstract these things, we're going to introduce this very nice notion called semantic properties. Okay. So let me define it. And please interrupt me with any questions. I know it's a bit harder to do in Zoom, but please do. So semantic properties are really asking, these are You should think of as, properties defined on programs. I give you a program and you're trying to tell me something about the code. I give you a text file, you give you a bit string, we interpret it as a Turing machine. I want to know something about the Turing machine, right? And we say that it's a property if it only depends on the, I'll make it formal, but let me just state it informally first. Functionality or input output behavior of the program or Turing machine. When I say program, you should really be thinking about Turing machine. Okay. Okay, so let me state it formally now. Formally, we'll call this semantic functions or properties. Both names are useful. So suppose, I have some function which takes binary strings as input and outputs just 0 or 1. Okay, and we will always think of the function interpreting its input as a Turing machine. Okay, so it's a function defined on top of Turing machines. Okay, and to make this precise, we first need to say that if I have two machines, two Turing machines, M, M prime are equivalent if for all x, M of x equals M prime of x. Okay, so meaning it's basically like saying, these two programs are equivalent in their functionality if the input output behavior is always exactly the same. Two Turing machines are equivalent if on any input x, both machines give the same answer. More concretely, like, if something doesn't halt, the other should also not halt. If one halts, the other should halt and end with the same answer as well. Okay. And we say that the function f is semantic if for all equivalent Turing machines, the answer is the same. Okay. So if I take two equivalent machines, the output of the function f is the same. So it only depends not on the specific Turing machine you're looking at, but on the input output behavior of the function of the Turing machine that you are building. We've seen several examples of semantic functions already. Can you give me one example of a semantic function? Any guesses? So what's a semantic? Yeah, eval. Well, eval, there's one technicality in that, the way we defined it, we are only looking at Turing machines. So let me, instead of eval, like, the input here is just a single M, right? Eval took M and the input to the original Turing machine. So syntactically, there's a small technicality, but, halt on 0. Is a semantic function. Right? Because it only depends on the functionality of the program. It doesn't depend on the exact encoding that you, like, the exact implementation of the Turing machine. Okay. And how about Any other examples? Well, not empty is also semantic. Why? If I have two machines, remember if I have M and M prime, right? And equivalent, then not empty of M equals not empty of M prime. Right? Because not empty is 1 when there is some x such that M of x equals 1. But then M prime of x should also equal 1 because M of x equals M prime of x for all x, and vice versa. Okay. So this is another example. Can you now give me a non-example of a function that's defined on Turing machines but is not semantic? You can easily modify things. I can say, okay, so non-examples. Okay, this is like a silly function, but here's the definition, right? I say f of m is 1. If I look at the encoding of the Turing machine, the last bit in the encoding is a 1 and is 0 otherwise. This is clearly, this is not a semantic function because there could be different Turing machine which has the same exact functionality, but the last bit is 0. Right? It should not depend on the exact way the program is written. It should depend only on the input-output behavior. Okay. So another example is, f of m equals 1 if m halts in 100 steps on 0. Okay, here's another function. It's a function which checks whether or not the Turing machine ends in 100 steps on 0 and is 0 otherwise. Okay, it is not semantic because the final output of a different machine could be the same, but it could run for a little bit longer. Okay, hopefully that makes sense. And let's look at another important example, like of how about the toddler function? Is toddler function semantic or not? So that's a little bit confusing, right? So let's think of what toddler does. So toddler of m is 1 if first bit okay. Now you can see here that it doesn't only depend on the functionality of m, because so hold on. So there's a question, can you give a high-level explanation of what semantic means? So semantic means you're defining, I'm giving you programs as input, and I'm trying to check whether the program satisfies some property. So the opposite of semantic is syntactic. I give you a program and I ask you, does this program contain the variable like foo? Does it contain the variable blah, right? So those are really depend on the exact instructions that you write down in the program, how the Turing machine is being actually implemented. Semantic is telling you whether or not the program's input-output behavior satisfies something. If I have two programs which have the exact same input-output behavior, I could have different lines of code which have the same input-output behavior. right? So then we need them to give the same answer. So for example, so recall we had this programs, these examples from, let me see if I can copy them. Okay, so this is a program M and this is a program M prime. Now, both of these are exactly equivalent, right? Because their input output behavior is the same on all the inputs, on all integer inputs. Okay, so F is semantic implies that F of M equals F of M prime. Okay, so it should not depend on the exact set of instructions that you have. Like, I might have some dummy variables, I might have a different algorithm giving the same input output behavior, but should only depend on the final answer. Like, for instance, imagine I ask you to solve some algorithmic problem, they're different, often students will come up with completely different algorithms which solve the problem, right? But every one of them is correct. Similarly, the semantic behavior should only depend on what the program is computing and not on the exact set of instructions that are inside that. Okay? Does that answer your question, Ethan? Okay. So let's go back to these examples, right? Essentially, whenever I can add some dummy instructions to the program and somehow change the behavior of F, it's not a semantic property. Toddler, on the other hand, looks semantic, but it is not semantic because it really depends on the encoding of the machine M that I use. Okay, so it is also not semantic. Okay, and one important class of semantic properties is kind of, I ask example. F of M equals 1 if M computes majority. Okay, so imagine I'm building, if I want to check whether I give you an input program and I want to check whether or not that program's functionality is exactly majority or any function, majority, parity, multiplication, addition, anything like that. If it only depends on the input output functionality, it is semantic. So F would be semantic. So you can call this equivalence with majority. Okay. All right. So that's the notion of semantic properties. And as I said, there are many areas within computer science which try to reason about semantic properties. Our goal is really to understand what, like, in compilers, for instance, I want to reason about whether or not this program is going to run, is it going to execute, is it going to lead to some bad behavior, and things like that. Okay. So there's this phenomenal theorem from many years ago, which is kind of a bummer, but it is what it is. It says that in terms of functionality, semantic properties are things that we really care about. And if we could compute them, that would be very helpful. It would be helpful in reasoning about programs. And there is this theorem, Rice's theorem, which says that unfortunately every non-trivial, I'll explain what this means, non-trivial semantic property is uncomputable. Okay. So there's a question, is Todd semantic? And the answer is no, Todd is not semantic, right? Because, so it's listed in non-examples, right? So it is not semantic because it depends on the explicit encoding of M. For it to be semantic, if I have two equivalent machines, M and M prime, then Todd of M should equal Todd of M prime, right? But that might not be the case because equivalence only talks about the behavior on same inputs. Okay, whereas toddler is kind of depends you know, so M comma M prime are equivalent doesn't necessarily imply that Todd of M equals Todd of M prime. Okay, doesn't necessarily imply, you know, it could be true, but you know, it doesn't always have to be true for all M comma M prime which are equivalent. So it is not semantic. But halt on 0, on the other hand, is semantic because it only depends on the behavior of the program on 0. Not empty is semantic. Equivalence, all those, that entire category of things is semantic. And so far, we kind of showed, okay, toddler is uncomputable, halt on is uncomputable, halt on 0, not empty. So we have 4 uncomputable things. But now Rice's theorem comes along and gives you a whole, like, you know, huge set, treasure trove of uncomputable functions, right? So basically saying any non-trivial semantic property is uncomputable. What do I mean by non-trivial? Basically something which is not the constant function, right? So not the constant function. Okay, so for instance, let's say I look at 1 from 0, 1 star to 0, 1, defined as 1 of M equals 1 for all Turing machines M. Okay, this is semantic, kind of tautologically, because it outputs 1 on all Turing machines. So even for equivalent ones, it is equal, right? And let's say 0 is just the same thing again, but outputs 0 on all things. Okay, these are semantic, but kind of they're trivially semantic. They're just outputting constant, and they are computable. Obviously, I can just always design a Turing machine which outputs 1, right? So these are computable, but any other semantic property besides these two, as long as it's not a constant function and is semantic, is uncomputable. Okay, so it's a very strong statement. It's saying no matter, there is no way around computing semantic functions. Okay, does the statement make sense? It's kind of very strong because it holds for all semantic properties, not for some specific things. And if you have this, obviously you can conclude from this that halt on 0, not empty, equivalence with majority, all these things are uncomputable directly from Rice's theorem. Okay. Okay, so let's try and prove this. And we will prove this by a reduction from halt on 0. So the proof is not complicated, but you have to kind of twist you have to think about things in a non-trivial way. It's not very long, but you have to kind of, think in a meta way as we've been doing always. So what do we really want to show, right? So suppose you have F is a non-trivial semantic property. It can be any non-trivial semantic property. For instance, it could be, okay, is my program equivalent to majority? Is my program equivalent to parity? All of those things. Okay. And we want to show that under this case, F is uncomputable. And we will show this from a reduction. So let's kind of set up some understanding of how to use this. So what does non-trivial mean? We have to use both of these things, right? Otherwise we won't be able to prove it. So what does non-trivial mean? It means that there exists some machine M0 and there exists some machine M1 such that f of M0 is 0. Okay. So basically it's saying, you have your space of all programs, all Turing machines, right? And here's F is kind of saying, okay, this machine is a 0, this machine is a 1, and so on, right? It's non-trivial means it's not a constant function. So there is some machine on which some input, which makes F output 0, and some input, which makes F output 1. Okay. So that's that we are getting from non-triviality. And now the proof is kind of clever in the following sense. We have to use some ingenuity here, and we're going to look at the following program. So idea, get a reduction. Okay, so I'm going to define a special program. It's going to be a silly program, but bear with me. It's called the infinity program. So what does it do? Actually, I don't even have to do anything. It's just a program which goes in an infinite loop. Okay. I'm just writing this a equals 0 as a placeholder, right? A program that goes in an infinite loop. Okay, so a Turing machine that does not halt. Pick any Turing machine that does not halt on any input. You give it some input, it completely ignores that input and just goes into a loop. Okay, so it does not halt on any input. Okay, and now we need a bit of a case analysis. All right, so case 1. So there are two cases, right? What does F do on this function? One case is the semantic property F classifies this as 0 for whatever reason. It could also say 1, it could say 0, it doesn't matter. Okay, let's do one case and then we'll go on to the other case. So now we are going to say that in this case, so under these assumptions, right, f is non-trivial, semantic property, and f of inf equals 0. In this case, we can reduce halt on 0 to f. Okay. What does this mean? So that is, we need a reduction such that for any Turing machine M, halt on 0 of M should equal f of R of M. Okay, this seems kind of very hairy, right? We don't know much about f. I don't even know what f is, but I'm telling you, you can come up with this reduction. How? Well, all we really need are these three things. That there is some m0, so that f of m0 is 0, there's some m1, and then this guy. Okay, can you give me some suggestions on how we might be able to come up with such a thing? How can I come up with this reduction? Right, so we need to come up with some R of M such that this equality holds for all machines. So one suggestion, let me give a hint, is idea. Suppose M is a machine that does not halt on 0. Then we want f of R of M to be 0, right? It has to equal, it has to be identical. The behavior should be, we want f of R of M, the reduction should also output 0, right? So then I'm going to say R of M should be equivalent to inf. On the other hand, if M halts on 0, then halt on 0 of M would be 1. The output would be 1, right? But for the equality to hold, we need f of R of M to be 1. But the only thing we really know about the semantic property is that there is some function, there is some program. It could in fact only be a single program for which this holds, right? So we need this thing to hold. So I want a reduction. I want a way to transform my input program M into two things in such a way that whenever M halts on 0, what I get is a program that goes into an infinite loop. If it does not halt on 0, its behavior is exactly that of M1. How can I do that? Any ideas? Okay, so let's see. So this is what we are hoping to do. Okay, when I write, let me now describe the reduction to do this. So R of M is actually going to be the following program. Right, so it's def n of some input z, and what it does is run okay, actually let me use x here. Almost. I think you're almost right. R can be universal Turing machine. We just want it to be something to exploit this non-triviality, right? We want to make sure that these two things hold. Okay. So let me now, this is the reduction that we're going to use. There are many other options to come up with, but this is one reduction, one way to do it. So it's just kind of two lines, right? Reduction, remember, is a way to transform one input to another input. So here I'm taking the input for alt on 0, and I'm defining a new program, which I'm going to view as input to my semantic property, capital F. And let's check the cases. So what do we need to show? So this is the what, right? So I define the reduction, and how part R is computable, right? So we are not running these eval functions. We are just kind of copying those instructions. We're just changing the text. So it is computable just as it was for when we were doing the reductions earlier. So, but why? Okay, so we need to now analyze why, right? So what does why mean? So if halt on 0 of M equals 1. So we need to show that this equality holds, right? The behavior of halt on 0 and F are identical. So suppose M actually halted on 1. What can you tell me about R of M? What is its behavior like? So if M halted on 0, then you would terminate in this step and go to the second step, right? So what does this tell me about the program R of M? What's, its behavior is equivalent to M1. Implies R of M is equivalent to M1. Okay. Any questions about this? So basically, we just have one line here, right? Whenever you halt on 0, you go to the next step. So I'm just running M1. Okay. Which in turn implies that F of R of M. Remember, F is semantic. Yeah, we should be returning M1 comma X. Oh, yeah. Yeah, that's exactly what I write. Maybe you mean I should be saying return here? Is that the question? Oh, yeah, we should be returning. That's what I meant by when I said that. Yeah, exactly. Right? So F is semantic, right? So its behavior, F of R of M should equal F of M1, which we know is 1. Okay? And on the other hand, if halt on 0 of M equals 0, then what happens? meaning m does not halt on 0. What is R of m equivalent to? So this new reduction program that we built is equivalent in behavior exactly to it's equivalent to inf, right? Inf is a program which goes into an infinite loop every time, right? And when halt on 0 of m equals 0, this program R of m also goes into infinite loop every time. It never gets to this second step at all. Okay. So okay. So therefore, we have the desired equality, right? There is a way to translate an input for m to an input for f so that you have the equality. Okay. So thus we have a reduction from halt on 0 to f. Implies f is uncomputable. Okay. So if we could solve f, we could solve halt on 0, but we cannot solve halt on 0, so we should not be able to solve f. Okay. So that's kind of the whole proof. Like it's a little sort of mind bending, but basically what you're trying to do is kind of exploit this dichotomy, right? I give you a program m and I ask you to check whether m halts on 0. Now I spit out a new program which has two behaviors. Like, when m halts on 0, its behavior is identical to m1. When it does not halt, you just get an infinite loop. Okay. And this is all happening in this case. And there's one more, we assume that f of inf is 0. Okay. And I can say we have to also handle the case where f of inf equals 1. Right? And it is not too difficult here. In this case, you can get a reduction from not halt on 0, but I'll leave that as an exercise from the homework. So let me say the idea is reduction from okay. So you can kind of do the same thing. We just have to slightly change things, but nothing materially changes. Okay. Any questions about this? So in summary, we have this very powerful theorem. So Rice's theorem is extremely powerful, as I said, because you can use it to now get like a zillion, an infinite number of uncomputable problems, right? Any non-trivial semantic property is uncomputable. Okay. So it's just a you can get all kinds of uncomputable functions, right? So for example, there is no automated way to do software verification, right? Rice's theorem just completely kills it. If I give you any program and I ask you to check, is it computing majority? There is no automated way to do it. Because I can just build up like this dummy simple trick, right? It's not even that complicated and make you solve halting problem. If someone comes and says, okay, this function is actually going to compute parity, that's good, but there's no way to verify it. There's a question, is there a way to prove that a function is semantic? Yeah, so you have to prove it mathematically. Like, you can basically show that it only depends on the input output behavior. Meaning whenever, and it's also very formal, right? Equivalence is formally defined, which is, if I have m and m prime such that m of x equals m prime of x for all x, then f of m should equal f of m prime. And that's a formal definition. So you can actually verify it always. Okay. So uncomputable. All right. Any other questions? And one should keep in mind that, this gives you dozens, as I said, many uncomputable problems, kind of really kills the hope for meta reasoning about programs. Any property that you care about, it just cannot be solved on a computer. Any property you care about programs cannot be answered by a program. Okay. So let's take a 5-minute break. And when we come back, we'll see why this theorem is such a buzzkill and ways to get around it. Okay. All right, let's take a 5-minute break and we'll resume at 1 o'clock. Okay. So let's summarize our discussion of Turing machines, right? We started this about 2 weeks ago. So we started by defining this new model of Turing machines by extending the notion of DFAs in 2 natural ways, right? We said, okay, DFAs were limited to make only a single pass on the data. So let's allow it multiple pass. And then we also said, let's allow it memory, long memory. Okay, that was the notion of a tape, and that led to the definition of Turing machines. And we saw examples that they could do things which are not possible by DFAs. And I stated without proof, this theorem, that Turing machines can actually simulate Python programs. We didn't prove it, but that is true. And this is a theorem that we can actually show formally. And then we went many steps ahead and formulated this hypothesis, that something that we think is true about nature, about the universe that we live in, is that Turing machines are really the model of computing, in the sense that anything that is possible to be solvable by a physical computational device is possible to be solved by a Turing machine. Like, for instance, Turing machines can simulate quantum computers, whatever they are, and all kinds of other crazy computational models. They are simulatable by Turing machines, at least anything that we have so far. That's the Church-Turing thesis. And then we also had this notion of universality, right? And again, this was a formal thing that we proved, saying that there is a single Turing machine which can simulate any other Turing machine, right? You can view a Turing machine as the description of the machine as input to this other machine, and we can solve it. And finally, we also use this interpretation of code as data, viewing the input to the machine as a machine itself led to all kinds of weird circular things. In particular, it led to our first uncomputable problem, the toddler problem. And starting from toddler, we built this web of reductions, right? We started with toddler is uncomputable. And from there, we went to halt is uncomputable. And from there, we went to halt on 0 being uncomputable, to not empty. And finally, we also had Rice's theorem. Right? All semantic properties, all non-trivial semantic properties are uncomputable. Okay. So there is like a good and bad side to Turing machines. Right? They are very powerful. You can do all kinds of things that we care about on Turing machines. You can multiply, add, write programs in it for any task that we think is possible. But on the other hand, this great power comes with great restrictions on reasoning about programs. If your model of computation is very powerful, then your ability to solve questions about those programs on computers is limited. Okay. So in some sense, we also talked about this notion of Turing completeness. Right? You can try and come up with restricted languages, models of computation, but more often than not, things become more often than not, they become Turing complete. I mean, people have built Turing complete models based on something out of Super Mario games. Okay, so you can build all these programming languages which are all Turing complete, which in some cases can actually be a feature, right? I want a powerful model of computation, which is great. But also sometimes it can actually be a bug, right? A feature. Can use it to program anything. Why could it be a bug? Well, I can't program anything, and more importantly, a bug because reasoning about programs becomes unsolvable. Okay, and this is a real world scenario. It's not just like a huge, some thing that we care about in theory. This bug can be devastating in practice. So for instance, there is this whole story about Ethereum, the cryptocurrency. So they had an instrument to do some kind of contracts, digital contracts, which they call DOA, digital contract market. Okay, so they wanted to build this whole new market based on cryptocurrencies and based on blockchain technology to be able to do contracts online in a decentralized way. And at the height, this whole thing was running on Ethereum. You allocated Ethereum coins for it, and it was worth $150 million. Okay, and as part of it, they actually introduced a new language to build these contracts, and they said, it's kind of sound, we cannot do weird things in it, but some hacker, or you might call that person a wise investor, or some person who actually took a CS 181 course in their life figured out that this language actually is Turing complete. So they found a contract that loops forever. And they used it to basically transfer $60 million into their own fund. Okay, so they found this bug basically, which kind of a subcontract, which was making the whole contract system loop forever. And as a result, like, they were able to siphon off $60 million, which is a huge money, and also like a huge chunk of the market DOA. And then there was this whole split about Ethereum, the whole currency split into two segments, there's Ethereum Classic and Ethereum, the new Ethereum, and so on and so forth. So a lot of debate on whether or not they should have done it, and they should have just given this person that much money, but that's another story. Okay. So the punchline here is that Turing completeness can both be a bug and a feature. Sometimes, I want to actually design a programming language for which asking these meta questions, checking whether or not the program could cause me to go into an infinite loop on some input is decidable. I want to prevent people from uploading programs on my server which will make them run forever. How can I do that? One way to say is that, okay, you are not allowed to use for and while loops at all. And maybe you avoid all kinds of go-to statements and all kinds of things like that. Maybe then you can avoid it, but then are you limiting the power too much? Okay. So this motivates the question of studying restricted computational models. So I want to design restricted computational models, things which are going to be more limited in power than Turing machines, but useful for some specific purposes. And I can still answer at least some of the meta questions that we care about, right? And this is a perspective we are going to take towards one very important class of models, for which we can answer some of these meta questions and also are important by themselves. And that's the model of context-free grammars. Okay, so as we will see, we can actually check whether or not, first of all, they're interesting by themselves. They play a very important role in programming languages and linguistics, and some meta questions like halting problem, checking whether the language accepted by machine is empty or not empty. Those things are actually computable for the case of context-free grammars. Okay, so we'll abbreviate them as CFGs. And you should really think of them as intermediate in complexity compared to DFAs. Okay, so DFAs are the most primitive ones. They are going to be less powerful than context-free grammars, which are less powerful than Turing machines. All right. So with that, let me now define context-free grammars. It's also kind of a fun model to play with. Okay. So what are context-free grammars? So when I'm going to write it down formally, it might seem a little tedious, but when we see examples, things will become clear. And unlike the case of DFAs and Turing machines, for context-free grammars, let me define them over slightly more general alphabets because many applications, especially in programming languages, compilers, and linguistics, people do study non-binary inputs in the context of context-free grammars, and it's not going to be much more complicated. Okay. So a context-free grammar G is really a 4-tuple. So you have some set V, some space, some alphabet or space of terminals, some R, which is going to be a set of rules, and S. Okay, I'll tell you what these are in a bit. So V corresponds to variables, is alphabet / terminals. You should really think of them as just 0, 1. Okay, maybe 0, 1, yellow numbers 2, 3, letters A, B, C, D, and so on and so forth. So R corresponds to rules. Okay, and S is start. Start variable, not symbol, but start variable. Okay. So context-free grammars are essentially rules for substitutions. Okay. And one thing we should keep in mind is that sigma is disjoint from variables. Okay. So I'm going to describe this essentially by examples instead of stating them formally. Okay. So example rule. A rule really is of the following form. It takes a variable and gives out a string in this. Okay, so a variable, actually let me write it this way, a variable to Z, where Z is an element of sigma union V star. So given a variable, a rule allows me to substitute this variable with any other string. It depends on what rules I specify, but the string can contain either terminals or new variables again. Okay. And you have this variables, terminals, a sequence, collection of rules, and a start symbol. Okay. So let's do an example. So the grammar is the following. I tell you it's there's only one variable, A. The space of terminals is just 0, 1. R, I will tell you the start symbol is just A. The starting variable is just A. And what are the rules? Rules are A can be substituted with 0, A1. Okay. Or A can be substituted with the empty string. Okay, so this is a grammar. Let's say any questions about this? Basically, you have a variable. I can substitute with any sequence on the right-hand side. And here, as an example, I'm saying you can replace A with 0, A1 or A with as an empty string. It's an example of a grammar. So far, I've just told you what this object is. It's this 4-tuple. You have some variables, some terminals, some rules, and a starting symbol. Okay, but what do you do with them? So the main things you do with them are get derivations. Okay, And there are two kinds of derivations. Once again, when we look at these examples, things will become clear. So derivations meaning, suppose I have a sequence which is a combination of variables and terminals. Okay. And I have a sequence of variables and terminals again. We say alpha implies beta, or within the grammar G, we can derive the string beta from alpha if okay. We will say we can derive beta from alpha if there is some rule which when I apply to alpha, I get beta. Meaning there is some variable, I look at that variable, I replace that variable according to what the rule says, and then I get the string beta. Okay. So for example, for the grammar above, I can say that the string 0a implies, so let me maybe call this G1, implies 00a1, right? Because this is my alpha string, this is my beta string, and I can get the new string beta by applying the rule a to 0a1. Okay, so I'm just replacing, oh, sorry, we can get beta. Thanks. Definitely. So we should be able to get beta by replacing a variable in alpha. All right. You know, another example is 0a implies just 0. Why? I could apply the rule a to epsilon, you know, just replace it with the empty string. So I get this. I can go on like this, you know, I can say 00a1 goes to 001, or 00a1 goes to, or let me remove 10 here. Okay, so all of these are examples of derivations. So we're just doing one application of the rule where I replace one variable with another. Maybe let me color code it. And you can do it even with multiple variables, right? You know, I could have, let's say, AA. I can say this goes to 0A1A, right? You know, I'm essentially replacing this A with this guy here. In the same way, I can also say AA goes to A0A1. Right here, I'm replacing the second A by the first rule. Okay, so all of these are valid derivations. Okay, so now we can chain these derivations one after the other. We kind of define one step of a rule, but I can keep applying the rules again and again to get new and new strings. You should really think of it as a programming language where I'm manipulating strings. I start with some sequence, some string, and then I replace some portion with another string, I get something, then I repeat it again and again. So this leads us to the more extended notion of derivations, where we say if I have a grammar G, then the single implication is applying one rule. And when I put a star, that means I can apply the rules again and again. Okay. So if there exists a sequence of derivations to get beta from alpha. Okay. In other words, there exists some, alpha 1, alpha 2, up to alpha L minus 1, such that, I'm basically chaining things. I apply one rule to get alpha 1. I apply another rule to get alpha 2. I apply another rule, alpha 3, so on. Finally ending with beta. So all of the rules are in the same grammar. By chaining these things, I'm going from alpha to beta. And so we're kind of forgetting what happened in between. I'm just storing whether or not the string beta can be derived from alpha. Okay. So let's see an example of this too. So we have our grammar G1 above, right? The same grammar with this just two rules, right? A to 0, A1, A to epsilon. Now I can say that, well, A implies star why? Well, I can go from A to just 0, A1. That's one application of a rule. And then I do the same thing again, and I get 0, 0, A, 1, 1. Right? So this is valid. And similarly, I can also say okay, this is also valid, right? I'll just keep replacing the first one. So I say AA, apply one rule to get 0, A1A, apply it again, I get 0, 0, A11A, apply it again, I get 0, 0, 0, A111A, and then apply the epsilon rule. Okay, so we can always define these relations. So why are we defining these things? You have the substitution rules, but the main reason we're doing this is we can think of it now as a computational model. Okay, meaning we'll think of this grammar in some sense like a regular expression, loosely speaking. We have some set of rules and we can use it to define a computational model. So given a grammar G and a string X now defined over sigma star. You can think of sigma just as being 0, 1, so then it's just binary strings. But I just wanted to be a bit more general for context-free grammars because it's somewhat useful here. Is matched to the grammar G. So we say a string X of terminals, remember sigma is like terminals, of terminals is matched to or matched by, people, you can use different terms, if if starting from this start variable of the grammar G, I can derive the string X by chaining up these rules. You start with the starting variable by chaining up all of these things in various ways. I get the string X. Whenever that happens, we say that X is matched to or by the grammar G. Okay. Any questions about this? So we can also, just in terms of terminology, say that given a grammar G, we define a function. Just like we define a function for regular expression, where fg of x equals 1 if x is matched by G and 0 otherwise. Okay, I give you a string of terminals. You can tell me whether or not the sequence is derivable from the start variable. If it is derivable, then the function output is 1, otherwise it's 0. Again, these are different terms, different names for the same thing. We have a function. We can also define the language. Of the grammar as all those strings which are derivable from the start variable. So I should say this is X is a string just of terminals such that X matches G. Okay. And these are called context-free grammars. Any language for which there is a grammar which can match it is called a context-free grammar. Okay, so these are called context-free grammars. Context-free languages. You might wonder why the context-free appears. The intuitive reason is that in the rules, the left-hand side of the rule only depends on a specific variable. It doesn't really care about what's around it, right? So whenever you see a variable, you can just replace it irrespective of what's around it in the string alpha. So in some sense, it's like not taking into account the context or what is around the specific variable where you're applying the rule. So that's why it's called context-free grammar. But that's kind of some old distinction, which is not too important for us. Okay. And finally, we have a computational model now. So a function f from sigma star to 0, 1 is context free. We say it is context free if there exists a grammar G such that so just as we said, a function f was regular if there was a DFA such that the DFA computed exactly that function. We say a function is context free if there is a grammar which computes that function. Okay, so we introduced a completely new model of computation now. All right, any questions about this model? Okay, so let's go back to the example that we had earlier. Right, so let me copy it over here. Okay, so let's do an example. So we have this grammar. What is the language computed by this grammar? So what strings? So remember the terminals, the alphabet is just 0 1s. So the language is subset of just sigma star, right? It's only going to contain binary strings, but what's the language computed by this grammar? What strings are derivable from the starting symbol in this grammar? Any guesses? Well, it's actually, you can kind of do a few examples and figure out that basically what you're doing is every time you're replacing A, I apply the first rule, I get a matching 0 and 1. Replace it again, I get another 0 and 1 and so forth. And when I replace it with epsilon, the process ends. Okay, so the grammar computed by this, the language computed by this grammar is exactly just this. All strings which have, a string of zeros followed by an equal number of ones, that's the language computed by this. Okay, so every time we apply rule 1, we get a 0, 1. Okay, and so on and so forth. Okay, let's do one more example. Okay, so again, I'm going to have a single start symbol, which is A, and the rules are slightly different from what we have here, which is A is going to go to 0, A 0. A is going to go to 1, A 1, and A is going to go to epsilon. Okay, so these are the only rules. Oh, sorry, actually, I want to add more rules. Just constants. Okay, so I have 5 rules now. A is going to 0, A 0, to 1, A 1, to epsilon, and 0, 1. Exactly. So the language computed by this is just palindromes. Again, you can check by examples. So what's happening here is that every time you apply either of these 2 rules, I'm creating a 0 at the ends, right? So they're always matching. And in the middle, I'm substituting either with a single epsilon or a 0 or a 1. So LG is all X such that X is a palindrome. Okay, and you can already see that these 2 are actually non-regular languages, right? So context-free grammars, context-free languages are at least, not contained in regular languages. These are 2 languages which we know are not computable by DFS, but are computable by context-free grammars. Okay, and one notational convention. So when we have multiple rules with the same variable, you kind of shorten them so that things become easier to write down. So let's say if we have multiple rules, maybe A is going to some Z1, A is going to Z2, A is going to Z3. We write it for shorthand as just A is going to Z1 slash Z2 slash Z3. Okay, meaning I really have three rules where I can replace A with Z1, A with Z2, or A with Z3. This bar is just kind of meant to do that. Okay, so if I were to write this in this notation, I would get something like this. Okay, so I can rewrite it just as we have G2, which is, there's only one variable. I have 2, 0, 1 set of rules. The starting symbol is A, and the rules are A goes to 0A0, 1A1, 0/1/epsilon. Okay, so I have 5 rules. I just wrote them in one line with epsilon, this bar separating them. Okay, so let's do one more example. This one is a bit more refined. My variables are going to be, I still have only one variable. Say S. Sigma is let me use square brackets, maybe actually let's just do this. Yeah. So sigma now is parenthesis. So basically I'm looking for sequences of opening and closing brackets. And my idea is to only have those things which are well-formed parentheses, right? You might have seen this before, like, this is a valid sequence of parentheses, meaning there's an opening, closing, there's a way to match them together. And this is valid, somehow this is valid. This is also okay, but this should not be. This is also valid actually, but if I do something like this, then this is not well formed. Somehow I cannot match them in an appropriate way, right? So these are my sigmas, starting symbol is S. What are the rules? And there's only one variable, which is the start. Okay, so the rules are just the following. This is possible. I can, given a well-formed expression of parentheses, I can form a new one by enclosing new brackets, or I can do S and S. I can always do something like this, or I can just replace it with epsilon. This is a new grammar, and what's the language computed by this grammar? All strings of well-matched okay. So you can see that context-free grammars are seemingly quite powerful, right? You can just have 3 rules here, and somehow generate all well-matched parenthesis expressions. Okay. And that's one of the reasons why people studied context-free grammars. They are really critical in programming languages. Okay, so let me finish with that. So why context-free grammars? In linguistics, people try to model languages like, can I build a context-free grammar for English? Unfortunately, you cannot, because this context really depends. Can I write down a set of rules which would generate all grammatically correct English sentences by using context-free grammar? That's not quite possible, but at least for all programming languages, we can. You take C, Java, any language, Python, whatever you might have. So for all of them, there exists a grammar G that generates syntactically valid programs. Okay, so meaning there exists a grammar, some set of rules, G Python, such that P is a valid program if and only if P belongs to L grammar. Okay, and this is not just an existential statement. In fact, the formal specification of these programming languages is by coming up with this set of valid grammar rules. Okay, and you might have heard of parsing programs, in compilers. That's actually happening by looking in the underlying grammar and doing something to get out the corresponding tokens and so on. So we are not going to dig into that at all in this course, but context-free grammars are central in the area of programming languages, especially in designing all these programs and building compilers. Okay, but what we are interested in is what is the power of this context-free grammars? What is the power of the languages? What kind of languages can you generate? Can you compute using context-free grammars? Can they compute everything? At least seemingly, they are more powerful than DFAs already. They can do palindromes, they can do the 0 to the n, 1 to the n, which we know is not regular. But it is not clear that they are as powerful as DFAs. Maybe they can't do regular languages. Can they do all regular languages? We are not sure yet. Can they generate all strings which have an even number of ones? We don't know, but we will figure that out in the next lecture. And we'll also see that context-free grammars are actually a restrictor model of computation for which we can answer meaningful questions about grammars. If I give you a grammar as input, you can tell me whether or not, the grammar's language is empty. You can solve the halting problem for grammars, as we'll define and study in the next lecture. Okay, so let's stop here and I'll see you all on Monday.